Organic chemistry. Now, if that word makes you a little nervous, don't worry. We're going to treat it less like a tough subject to memorize and more like what it really is, a logical, elegant blueprint. It's a set of rules that lets us understand, predict, and even build the very molecules that make up our entire world.
We're going to follow the exact journey a chemist takes. We'll start with the molecular blueprint, its structure, then figure out how it'll react. After that, we'll jump into the lab to make it, clean it up, and finally, prove that we actually made what we set out to create. It's this really cool, complete life cycle of discovery.
You see, at its heart, organic chemistry isn't just a random collection of facts. It's a continuous, logical cycle. What we understand about the tiniest microscopic atoms lets us predict how things will behave on a scale that we can actually see and touch.
And this diagram right here, this is our roadmap for the whole process. It all kicks off with structure and bonding, basically what a molecule looks like in 3D. That structure then tells us about the reaction mechanisms, or how it's going to interact with other molecules. So once we run a reaction, we have to perform purification to get our product all by itself. And finally, we use analysis to confirm what we made, which circles right back and proves our initial understanding of the structure was correct. See that loop? It's a really powerful process.
So let's begin right where it all starts, with the fundamental architecture of the molecules themselves. Before we can get into how they act, we've got to understand how they're built.
The really incredible thing about carbon is just how versatile it is. Think of an atom's electrons as living in these little rooms called orbitals. Well, carbon is like a master architect. It can actually remodel these rooms, mixing them together to form new hybrid orbitals. For example, when it mixes one s orbital and three p orbitals, we get what's called sp3 hybridization. And bam, this creates a perfect tetrahedral shape like you see in methane. But if it only mixes one s and two p's, you get a totally flat planar molecule like ethene. And mixing just one s and one p gives you a perfectly straight linear molecule like ethine. This one idea, hybridization, is literally the secret to figuring out a molecule's 3D shape.
Okay, but how in the world do we draw these 3D shapes on a flat screen or a piece of paper? Well, we use a special kind of code. A regular line means the bond is flat on the page. A solid wedge means that atom is popping out towards you. And a dashed line means it's going away from you into the background. It's a simple, universal language that lets chemists everywhere instantly see a molecule's 3D structure. Pretty neat, right?
And this shows the two sides of a molecule's identity perfectly. Over on the left, we have the functional group. You can think of this as the molecule's chemical personality. It's the part that does most of the heavy lifting in reactions. Then on the right, we've got its official name from the IUPAC nomenclature system. This isn't just a random name, it's a code. The prefix tells you about any branches, the parent chain tells you how long it is, and the suffix identifies that super important functional group. It's a universal language that links a name directly to a structure.
All right, so now that we've got a handle on structure, let's get to the action. How do these molecules actually interact, transform, and create new things? Welcome to the chemical dance of reactions.
So for any reaction to happen, bonds have to break. Think of a bond as two people holding onto a pair of gloves. In what we call heterolytic cleavage, one atom gets greedy and just takes both gloves, both electrons. It becomes negatively charged, leaving the other one positively charged. This creates ions. But in homolytic cleavage, they split the pair fairly. Each atom takes one glove. This creates neutral but really unstable things called free radicals, which are just dying to react with something.
So what actually drives these reactions? Well, most of the time it's just a simple attraction. On one side, you've got nucleophiles. The name literally means nucleus-loving, and because they're rich in electrons, they are always looking to donate a pair. On the other side are electrophiles, or electron-loving species. They're poor in electrons and are eager to accept a pair. So the electron-rich nucleophile acts like a key, always searching for the electron-poor lock of an electrophile. This fundamental push and pull is the engine behind countless organic reactions.
And while there are millions of different reactions, they almost all fall into one of just four main categories. In a substitution, one part of a molecule gets swapped for another. And in addition, two or more molecules combine to form a single bigger one. Elimination is just the opposite, where one molecule splits into two smaller ones. And finally, in a rearrangement, a molecule just kind of shuffles its own atoms around to form a new structure without adding or losing anything.
Okay, so we've designed our molecule, and we've run the reaction in the lab. But here's the thing.
Chemical reactions are messy. You always end up with a mix of your product, side products, and leftover starting materials. So the next critical step is to isolate the one pure compound that we actually want.
So how does this work? Well, chemists use clever techniques that take advantage of simple physical differences between compounds. Take distillation, for example. It separates liquids that have different boiling points. You just heat the mixture, the liquid with the lower boiling point turns to vapor first, and then you can cool it down and collect it in a different flask, pure. Differential extraction uses two liquids that don't mix, like oil and water, to pull your compound from one liquid into the other. And sublimation is a neat trick for solids. It turns the solid you want directly into a gas, leaving impurities behind.
Now, for really precise separations, the gold standard technique is chromatography. The basic idea is that you have a mixture flow past some kind of stationary material. In absorption chromatography, different parts of the mixture stick to the material with different strengths, and that's how they get separated. In partition chromatography, it's more about how the components distribute themselves between two different phases. It's an incredibly powerful tool for getting things ultra-pure.
All right, we've made it and we've purified it. But how do we know for sure what we actually have? This is the final, crucial step, analysis. This is where we gather the evidence to prove that the molecule we're holding in our hands perfectly matches the blueprint we started with.
An analysis is really a two-step process. First up is qualitative detection. This asks the simple question, what are the ingredients? Which elements are in this thing? Then comes quantitative estimation, which asks, okay, what's the recipe? What's the exact percentage of each of those elements?
That first question, what's in it, is often answered by a classic procedure called Lassigne's test. It's a really clever method to break the compound apart and turn its elements into simple inorganic forms, which are much easier to detect with basic chemical tests. It's the first step to finding out if your molecule has key elements like nitrogen, sulfur, or halogens.
So once we know what's in there, we need to find out how much of it there is. And chemists have some very precise ways to do this. As you can see in the table, we can figure out the amount of carbon and hydrogen by carefully burning a sample and weighing the CO2 and water it makes. There are other specific methods for things like nitrogen and halogens, but my favorite is the trick for oxygen. Often chemists measure everything else, add up the percentages, and just assume that whatever's missing to get to 100%, well, that must be the oxygen. It's a simple process of elimination, but it works.
And with that, we have come full circle. We've gone from a theoretical drawing on a piece of paper to a real, purified substance whose identity we have confirmed. Let's put it all together.
This is the whole shebang in one image. We started with the microscopic blueprint, the structure. This let us predict the reactions it would go through. Then we moved into the macroscopic world of the lab, using purification to isolate our product. And finally, analysis gave us the hard data that confirmed its composition, which fundamentally proves that our initial structural model was correct. The loop is closed. The blueprint is complete.
So, what are the key takeaways from all this? Think of these as the essential tools in any organic chemist toolkit. First, molecular shape is all about orbital hybridization. Second, every structure has a unique, logical name from the IUPAC system. Third, most reactions are just a dance between electron-rich nucleophiles and electron-poor electrophiles. Fourth, all those reactions fall into just 4 main categories. And finally, lab techniques like purification and analysis are what connect our ideas to reality.
We've just explored the fundamental logic of organic chemistry, a blueprint for understanding and building the molecular world around us. This knowledge isn't just an endpoint, it's a foundation. It's the toolkit that's used to create medicines, new materials, and all the technologies that shape our lives. So the only question left is, now that you have the blueprint, what will you build with it?